Hello everyone, I'm Elena Lubimtseva and this is Unit 2, Climate Modeling in Environmental Studies and Geography for 12, Global Climate and Environmental Change. In the second unit, we will focus on the introduction to and history of climate modeling, AOGCMs, the Atmosphere, Ocean, General Circulation Models, global and regional climate change scenarios, and the IPCC stress and RCP policy scenarios. Climate models are very complex computer simulation models that help scientists to ask questions and understand what would be climatic conditions and what would be the weather patterns under those conditions in different parts of the world. Here are some examples of the questions that models can help us to answer. How will temperature or precipitation or atmospheric pressure or any other variable that is describing weather today, how is it going to change for a given emission scenario under new climatic conditions? What are the uncertainties of those projections? What should we do in order to stabilize carbon emissions into the atmosphere, and how we can stabilize the concentrations under those future scenarios of carbon emissions? How climate patterns is going to change, how climate patterns are going to change regionally, and what will be the seasonal changes in those climate patterns? How climate variability is going to change? What will be the weather extremes under these new climate regimes in different parts of the world? How different would be the results from different models? If we compare climate change scenarios from different models, we can see if they agree or disagree. And this is part of the way how we can also say how reliable those scenarios. However, climate models can be run not only into the future, we can also run them into the past and into the present. And this is how scientists actually can verify how reliable are those models, what is their quality in predicting future climatic conditions. When scientists run those models into the past, they compare them to the real data from the meteorological stations, or if the climate simulations are ran for the present day, again, we can compare those simulations to the real life data and then see if the model estimates climatic conditions or not. Climate models can also help us to determine probabilities of changes in various climate variables. For example, an increase or decrease in precipitation, or increase or decrease of runoff or other variables in different locations. In the previous unit, we have discussed the Earth climate model, and we spoke about various processes and coupling of different parts of climate system. For example, coupling between the atmosphere and land, or atmosphere and ice, or atmosphere and ocean. Those processes can be described as systems of mathematical equations, and this is how the model is describing what is going on in the entire climate system. There are three levels of complexity or spatial dimensions that are used in climate modeling. The first, the simplest level of complexity, are the so-called one-dimensional or 1D models. Examples could be radioactive convective atmospheric models, or upwelling diffusion ocean models, or energy balance models. All these models are focusing just on one dimension, for example, just altitude in the atmosphere, or just latitude on the surface of our planet, or just depth in the ocean. They might be exploring how the temperature is changing, or how the solar radiation is changing within this dimension, how the water is moving upward in the ocean as it gets warmer and becomes expanded, again, in connection just with one spatial dimension. The second level of complexity are 2D or two-dimensional models. Again, they can be used for modeling the ocean, or they can be used for modeling the atmosphere, or sometimes even both. And they explore the relationship of variables within two dimensions. For example, latitude and altitude in the atmosphere or height, or latitude and depth in the ocean. We can look, for example, at the behavior of the temperature in connection with latitude and altitude in the mountains at the same time. And finally, the 3D models are the so-called AOGCMs. Those are the atmosphere and ocean. General circulation models, those are 3D models because they take into account 3 dimensions, and those 3 dimensions can be latitude and longitude, and either altitude in the atmosphere or the depth in the ocean. Those are the most complex models spatially, and this is what is used today for global climate modeling. So when we are referring in this class to modeling scenarios, we would be actually talking about the scenarios produced by those 3D dimensional models or AOGCMs. The history of climate modeling is going back all the way into the 70s and 80s when, of course, the models were much simpler than they are today. Nowadays, we have significantly higher computational power, and the climate models have evolved tremendously during the past decades. Talking about the history of climate models, I want to mention sort of the previous steps of climate modeling, again, going back to those much simpler ways of representing climate systems. Some of these earlier, older models include energy balance climate systems. Those are one-dimensional climate models that help us to explore the relationship between the energy parameter and the latitude. Of changes in the incoming solar radiation between the equator and the polar regions. The radioactive convective models, or RCMs, is another example of one-dimensional models. They explore convective processes in the atmosphere or upwelling processes in the ocean as a one dimension which is related to the altitude in the atmosphere or the depth in the ocean. Another example of simpler climate models are statistical dynamic models, the SDMs, that can be also very useful for understanding statistical relationships between different climate variables. None of them is an equivalent of AOGCMs. So these models are very interesting and they all have their uses. But for understanding climate systems today, we need much more computational power and we need much more complex models. And so these models are referred to GCMs or general circulation models. They're called this way because they represent the circulation in the atmosphere or circulation in the ocean or both, and altogether they are portraying what is happening in the climate system at a given moment. The GCMs, or general circulation models, simulate the climate system using systems of mathematical equations that describe the Earth's radiation budget and its translation into heat and motion and the operation of the water cycle in the atmosphere and between the atmosphere and the ocean and land. If you think about how the climate system is represented in the general circulation model, you can think of it as cubes equivalent to pixels on your computer. So this is a 3D rather than 2D representation. So pixels would be 2D blocks, but those are actually voxels, the 3D blocks. And so the entire climate system, including the atmosphere, but also the ocean and the land and the ice, are represented as these mini blocks. And they're actually not so small. They can be several degrees by several degrees, for example, 1 degree by 1 degree, or several thousand miles by several thousand miles of latitude and longitude and altitude. And so think of these kind of discrete units representing the entire climate system around the world. These GCMs today are pretty complex. So there are AGCMs that represent just the atmosphere, OGCMs that represent just the ocean, and then AOGCMs that represent both. And so all the contemporary climate models that we are going to talk about in this class, they're all actually AOGCMs, and they include not only the atmosphere and the ocean, they also represent other parts of the climate system, such as cryosphere, the sphere of ice, and some elements of biosphere, the biological sphere. So AOGCMs today can be coupled with the cryospheric models, the models that help us to understand how ice and snow and glaciers are evolving, as well as biospheric models and biogeography models that help us to understand the processes in the life vegetation, in soils, and the way how soils and vegetation then being a part of climate system, producing and participating in positive feedbacks between other carbon sinks and soils and vegetation. Again, here is a little bit of history of climate modeling. So when we think about atmosphere general circulation models, the atmosphere can be represented actually in two ways. Mathematically, it can be represented as a finite grid, as three-dimensional grids that we just saw on the picture. This is numerical modeling of vertical and horizontal processes in the atmosphere, where grids can be really thought as cubes or as those voxels. Voxels like an equivalent of pixels. So those are finite grid models that can describe, for example, the temperature or the amount of moisture in the atmosphere, the distribution of heat, cloud cover, and so on. Wind can be portrayed like two different dimensions. In the past, another approach was used for computing climate system, and these were the so-called spectral models. So spectral models are combining the horizontal grid with the representation of atmospheric fields as waves using the Fourier transformation in a way so that they represent different atmospheric parameters as waves, say temperature or cloud cover, and so on. Today, all the climate models that are used as AOGCMs, they're all finite grid models. Finite grid models are much more reliable. They provide very realistic computation of all these variables, and they require significantly higher computation effort. So the main reason why the spectral models were used in the past and the spectral models were less precise compared to finite grid models is because they were able to produce somewhat satisfactory result with less computation power. This is not really an issue anymore. Today, the computational power is sufficient to support the most complex, the most computer-demanding climate models, and so we will be talking in this class only about finite grid models and they're all coming from different climate change centers around the world, and we would be working with the results from top 20 models that are selected by the IPCC as the most reliable models. So let's take a closer look at AOGCMs, the atmosphere ocean general circulation models. Sometimes they're simply called global climate models, and the ways how they can help us understand climate change in the past, present, but especially future. So the two key submodels of those AOGCMs are, of course, AGCM, the atmosphere general circulation model, and the ocean general circulation model. For the atmosphere, all the climate models essentially focus on 6 basic variables, and those are surface pressure, wind, which is represented in the model by 2 horizontal wind components, the temperature, the moisture, and the geopotential height. And I'm sure that you are pretty familiar with the temperature and moisture and pressure in weather forecasts, right? Those are the same parameters that we use for describing climate. One new concept here could be geopotential height. So you can see that the geopotential height map looks very similar to the map of pressure, but what we see here is actually the altitude where the pressure is the same. For example, the isolines can show us the altitude of the pressure 500 millibars or any other chosen pressure. This is important for climate modeling. So for each of the smallest units in the atmosphere, these little cubes that we call voxels, sort of the three-dimensional pixels, the general circulation model would solve for each location hydrostatic equation, two equations for horizontal motion of air. This is basically how the wind is represented. The thermodynamic equation, the water vapor equation, and the mass continuity equation to capture all those connections between the temperature, the pressure, the moisture, to show the wind, to show the patterns of the atmospheric pressure. And then the second component of the AOGCMs are the ocean general circulation models, and they're really coupled together as one system. So you are already familiar with the thermohaline circulation, which is pumping water all the way around the globe due to the Coriolis effect and due to the gradients of temperature and salinity. You know that the warm water is moving up and cold water is moving down. At the same time, it's moving from the tropical areas to the poles, and then it's sinking there and is moving back to the equator. And of course, the gradient of salinity is based on the fact that water with higher salinity is much denser compared to fresh water. So the OGCM is focusing primarily on this upper layer of the ocean of approximately 70 to 100 meters deep. And this is an area where there is lots of variability and lots of mixing and lots of processes such as vertical diffusion in mid-latitudes. Basically, with the latitude, the heat is distributed with the depth of the ocean very unequally, and at the same time, water in mid-latitudes is cooler than water closer to the equator. Near the equator, we see the lateral advection. Basically means that warm water is kind of spreading equally at the same altitude, and then the three-dimensional ocean models are the component of AOGCM, and they focus both on advection and diffusion and all other processes of heat exchange in the ocean, and of course the interaction between the ocean and the atmosphere. Now we know already that of course the climate system is not just only ocean and the atmosphere coupled together, but it really includes also the biosphere, with vegetation being tightly coupled through the carbon cycles and other biogeochemical cycle to the atmosphere and the ocean, as well as the cryosphere, the sphere of ice. And so the cryospheric models are increasingly becoming incorporated into the AOGCM to simulate the processes in the ice, in the sea ice and the glaciers, and of course in the polar caps that are extremely important for our climate system. Those are the changes in albedo, and again the changes in the heat exchange between the atmosphere and ice, the ocean and ice, and the atmosphere and the ocean. So the snow cover, the sea ice, the glaciers, the permafrost are increasingly incorporated in those models. And there are some challenges associated with this, like it's very difficult to model wind, for example, over the ice, or model oceanic heat transport and ocean atmospheric heat exchange. But you can see how the models are becoming more and more complex. So they're kind of moving historically from separate atmospheric models and ocean models to then combining both, and then combining them with ice models, and then also now the biospheric models as well, the biogeochemical models. So we will talk about the biogeochemical models and biogeography models a little bit later in this class. So these two graphs help us to compare the temperature changes that are predicted by the best climate models that are combined through the SMEEP5 project. So this is the project that takes together all the top climate models from different climate centers around the world and actually computes how different and how similar they are, and runs different tests by the international modeling community. And so what we see on this graph is the comparison of the summary of projections that the models would run if they were ran into the past since 1880s till now. And these projections are compared with the real data from 3 different data sets. Those are observed data that you can see from NOAA, from Goddard Center, and from Hadley Center in UK. So as we overlay all this data, they really tell us how reliable are these modern experiments, because they fit almost perfectly with the temperature changes that are actually recorded in meteorological data. So this is based on all forcings. So it means that the models take into account both human impact on climate, and including burning fossil fuels, global warming, as they take into account the natural forcings as well. On this graph, we see only natural forcings. So again, the same models would be run without taking human impact on the account. And in this case, the models would predict that the temperatures right now should be somewhere here. Our temperatures would be actually more than 2 degrees lower than they are right now if we could subtract the human impact. And so if we compare again these predictions since the past by the models compared to the real observations, you would see that there is a significant disagreement. So really the only way how we explain this woman, especially since the middle of the century, it's clearly linked to anthropogenic climate forcings. Climate modeling has a huge value for understanding our future and how we can adapt, and also what we can do to mitigate and reduce concentrations of carbon dioxide in the atmosphere. Models can provide us with really valuable information about what to expect. For example, here we see different scenarios of sea ice in the Arctic under different concentrations of carbon dioxide. So if we simulate what would be the global temperature all over the world if the concentrations of carbon dioxide were, let's say, 4 times under the pre-industrial level, essentially we would have no polar ice caps at all, as you can see in this scenario. So the sea ice thickness has already declined dramatically. We saw from the real data here, for example, the comparison of the sea ice thickness in the Arctic between the 1950 and 2000s. And this is a very significant loss of the volume. Almost 1/3 of the Arctic is already gone. So then the models can help us to also make projections and see what will be the changes in the future. Here is another interesting example of the use of climate models. So they can help us to understand not only the changes in the temperature, but also in the heat index. So the heat index is essentially the temperature which is adjusted for the moisture conditions, and it tells us a little bit more about the impact of the temperature on human health. So here we see the changes in July temperature in southeastern United States under current concentrations, and then double and quadrupled concentrations of carbon dioxide in the atmosphere, as well as the heat index. And you can see that with the humidity, the heat index is growing significantly higher as global warming progresses compared to the temperature. So this is something that we need to take in to account as we are thinking about impacts of climate on health. Another example is, of course, the sea level rise. So what we see here are the changes in the sea level rise under double and quadruple concentrations of carbon dioxide as well. And as you can see that under quadruple concentrations, we see the very dramatic sea level rise. Essentially, half of the Florida and the eastern coast of the United States is going to be underwater. Another example, changes in the thermohaline circulation. Under double concentrations, we see quite a significant decline of thermohaline circulation and then recovery, sort of the reaching the new equilibrium with the gradients of temperature and salinity. Under quadruple concentrations, the models essentially project that the thermohaline circulation is going to shut down completely. And this is quite worrisome because the data in the Atlantic Ocean already suggests that the Gulf Stream is changing, it's slowing down. And so there's lots of data suggesting that as global warming progresses, we might see quite significant changes in the global system of ocean currents. And then another example is coming from the realm of the hurricanes. We have a really dramatic hurricane season this year. And there's a fairly strong connection between the hurricanes and the surface temperatures of the ocean. So as the ocean is becoming warmer, more latent heat is available for formation of the hurricanes. There is also more water vapor which is available. And climate models are not exploring the hurricanes. It's a very different scales. But what can be done, what they can provide us, is the information that can be used in the weather models for kind of tuning up our understanding of the likelihood of a severe hurricane season under those climate change scenarios. Another example coming from the realm of soils. So global climate models can also help us to understand how the soil moisture is going to change under future higher concentrations of carbon dioxide. So what we see here are the soil moisture changes under quadrupled concentrations of CO2 versus doubled concentrations of CO2 in June to August. And of course, we can use then the agricultural models in order to understand how this is going to affect individual crops and how it's going to affect their productivity and yield. Climate models such as Hadley model and GFDL and CSSIRO, those are different examples of global climate models from different climate research centers from all over the world. We don't need to memorize all those abbreviations, although I would always point you to the websites of those climate centers where you can read on your own more about those models. So these climate models are then increasingly integrated with the biogeochemical models, such as Century model or Dolly model, that integrate information about biogeochemical cycles and the way how soils and vegetation are responding to climate change and how then those responses are also affecting climate change itself. And the biogeography models such as MAPS and Biome and MC1 and Biomap, those are examples of biogeography models that help us to understand how global vegetation is shifting all over the world and how those vegetation zones, biomes, are changing as a result of the changes in the climate zones. So far, we have learned how climate models help us to understand how the climate system is responding or would respond to concentrations of greenhouse gases, and we can prescribe different concentrations and ask the model what will be the response. So we saw the scenarios, for example, for double or quadruple concentrations of carbon dioxide. The next step, which is extremely important for us to understand, is how do we know what would be likely those future concentrations of carbon dioxide and other greenhouse gases in the atmosphere. And in order to do it, we need to familiarize with the policy scenarios. So in the next part of my lecture, we are going to talk about the so-called stress and RCP emission scenarios that actually drive AOGCMs. They're not a part of the climate models. They are developed with the help of some other models, such as economic models and demographic models, to help us to understand, to help scientists to understand what are the drivers of the future emissions and how they're going to affect our climate. So here is again just a little bit of history. The IPCC published its very first assessment report in 1990, when it's for the first time expressed concern very cautiously that human activity, particularly burning fossil fuels, might be causing climate change. And at that time, it was not really fully understood how this is happening, but that was really the first report of the IPCC. And so since the time the IPCC published 5 major assessment reports, they're always published every 5-6 years. It's a whole cycle of processing lots of research and lots of scholarly literature from around the world. And in between, it's also published many special assessment reports. So there is a number of special reports, for example, special report on climate change and land that was published a year ago. So special reports address some specific issues, and then the assessment reports are published by the 3 working groups, and they're very complex and very comprehensive. And the first working group is always working on science. The second working group is working on impacts, vulnerability, and adaptation. And the third working group is working on measures for climate change mitigation. So since this 1990 first assessment report, the IPCC came to realization that we need to have a system in order to evaluate what is really going into those emission scenarios, and we need to come up with a framework that would be uniform and used by scientists around the world in order to help us to understand how the demographic trends, the economic changes, the choices in the energy choices that we make, land use, agriculture, how all these socioeconomic trends are translating into the carbon emissions. And then those carbon emissions scenarios are used to drive AOGCMs. So in 2000, the IPCC came with the so-called STRESS, the Special Report on Emission Scenarios. And this is one of the frameworks that we are going to examine here. The stress scenarios have been changed since many times. They have been tuned up. Those are not necessarily the same scenarios that were initially developed in 2000, but that's a conceptual framework. And so 20 years later, this framework is still very useful, even though the scenarios themselves have tremendously evolved, and of course their computation has evolved tremendously. So then since that time, there was the third, there was the fourth assessment report. They were all using those stress scenario assessment framework. And then in 2009, another approach was developed, which is used at the same time as stress, and those are the RCPs. The RCPs are the representative concentration pathways. And those are essentially storylines for the world, helping us to see the connection between what would happen, let's say, if we do, this and this climate policy, and what will be the concentrations of carbon dioxide and other greenhouse gases under this approach versus a different approach. What would happen, let's say, if we have a mixed energy portfolio versus if we have only renewable energy? What would happen if we have the population, let's say, 10 billion versus the population 7 billion, and what kind of policies are really needed to get us into this type of scenario? So the fifth assessment report that we are using in this class is primarily using RCPs, and so we are going to look at both RCPs and stress and compare them, and they're kind of overlapping. And of course, right now, IPCC is working on its sixth report, and it's going to be developing more scenarios, but the RCPs are going to be there. So as we are talking about the stress and RCPs and also the AOGCM scenarios, it's really important to understand the difference between projections and scenarios. So the climate projection is usually a statement about what is likely to happen several decades to centuries into the future under certain conditions, right? We can ask the model about what is going to happen, let's say, if we have 500 particles per million of carbon dioxide, what kind of climate system we are going to see. Scenario, however, is not a projection and it's not a prediction, like it's not a forecast, like we can have weather forecast for tomorrow. The scenario is more, it's a much broader concept. It represents an alternative. It represents a possible way in which the future may unfold. So the scenarios would never tell us exactly how it's going to be in 2050. It's really more a story that is likely that it's going to unfold under certain conditions. So here is the philosophical framework behind the stress scenarios, and I find it extremely useful, even though, of course, this is a huge simplification. So the stress framework suggests that we really see two major tensions in the world. One tension is between the economic and environmental priorities, and we hear about this still all the time. I think the world really was thinking along these lines much more in the 1990s and early 2000s when this framework was initially developed. I think today we understand that economy and the environment are not mutually exclusive priorities, and we really need both. Governor Whitmer was talking today at the Climate Council with other governors, and she spoke precisely about this, how we really need to, it's a win-win if we have good climate policies. This is also great for our economy. But just here for the modeling purposes, we would just assume that there is this tension between economic growth and environmental priorities. The second tension is the tension between global and regional priorities. So again, ideally, we should not have this tension, but we clearly see it in this country. We can see it in many other parts of the world. This tension between globalization priority and strong nationalism or strong kind of regional or local agendas. So within the stress scenarios, there are four major groups. Essentially, A1 is a priority of global and economic interests. The A2, it's economic and regional, and then global and environmental would be B1, and then regional and environmental will be B2. At the bottom of the tree, you see all these different driving forces that are creating these scenarios. This includes the population growth, the development of our economy, the development of technology, energy choices, land use, and agriculture. So those are just the very general background ideas of how this framework works, and essentially the projections of climate change depend heavily upon what will be the future human activity and what would be really this story of the humankind that would describe our future the best. So there are about 40 different scenarios within this framework, and each of them is making various assumptions about what will be the future greenhouse gas pollution and land use and other driving forces. And all these different scenarios can be organized into four families, and these families are really driven by those four possibilities of those four major storylines: A1, B2, A1, A2, B1, B2, economy and environment versus global and regional. And they contain scenarios that then describe different situations and different assumptions for the demographic growth, for the development of the economy, for the technological changes, and for the sociocultural changes as well. So here are some ideas behind the A1 storyline. So this is a family of scenarios. It's not just one scenario. We'll see many of them. But within this, all the scenarios fold into the idea that we are moving to the world of stronger globalization. This world is primarily driven by the priorities of economic growth. This is the world where we are going to see the global population reaching 9 billion by 2050, but then it will start declining. Precisely because of the globalization, we see the world that is evolving very quickly around the use of efficient technologies. There is a very quick spread of those new technologies, lots of sharing of information, and it is essentially very much convergent, westernizing world where we see more convergence of lifestyles and diets and income and waves of life among all the regions. Within this A1 family, there are three subfamilies, and they show us very different pathways of what might happen for the world. The first one is the most fossil fuel intensive pathway. It essentially means that we are going to continue being dependent on fossil fuels. And it looks like this is probably not going to happen. We see already that many parts of the world have achieved very significant transition to at least partial use of renewable energy. The second scenario, the second pathway, is more balanced emphasis of all energy sources, including both fossil fuels, but also renewables and nuclear. And this is really where I think we're heading right now. And then A1T suggests that we would move in this direction, emphasizing only non-fossil fuel energy sources. So this is essentially renewables and nuclear. The next possible storyline with a number of scenarios within this family would be A2. So you remember that A2 stands for economic development and regional priorities. So this is a scenario of a more divided world, which is more driven by regional or national agendas with less global initiatives and global agreements. And this will be the world characterized by more independently operating self-reliant nations. And we kind of see some of these trends happening right now. We also, under this scenario, we are likely to see higher increase of the population compared to A1, because we will see some regions of the world where there will be very fast continuous population growth. So the population is not going to stabilize under 9 billion. It's going to be significantly higher. We would see more regionally oriented economic development. We would see also more contrasts, more difference between different regions, and also because it's more kind of the scenario where every region or every country on its own, there will be slower and more fragmented technological changes, and there will be less improvement to per capita income compared to A1. This third subfamily, the third storyline, would suggest that the world would actually embrace more environmental priorities and is going to be more sustainable. But just like as in A1, it's also the world of globalization, and it's the world of converging priorities and collaboration among the nations. So in B1, we really see a more integrated world, but it's also the world which is more sustainable and more ecologically friendly. Here we see also rapid economic growth, just as in A1, but this is the growth which is more driven by sustainable technologies. And it's also the scenario with faster transition to service economy and information economy, with more transfer of information and knowledge and technology around the world, also with more integration. And as a result of this integration and westernization, we also see that the population is also going to be stabilizing after 2050 at the 9 billion maximum. So this is similar to A1. And it also suggests a reduction in material intensity and the introduction of clean and resource-efficient technologies around the world. So this is the scenario, which is really, sorry, not the scenario, the family of scenarios. This is the family that is emphasizing global solutions to economic, social, and environmental stability and sustainability. And of course, this is a much more environmentally friendly scenario compared to A1 or A2. And then finally, the fourth group is this group B2. The B2 scenarios suggest that this is the world which is also more fragmented, more nationalistic, like more regionalized, less collaborative, like in those one scenarios, but it's also more environmentally friendly world. So it's sort of the world of this local sustainability initiatives going in somewhat different directions. Because it is a fragmented scenario, regional scenario, it also emphasizes continuous increase of the population. So it's less environmentally friendly compared to A1 or B1 in the sense that we were going to see here more population growth, but it also emphasizes local rather than global solutions for economic, social, and environmental stability and sustainability. And compared to A1 and B1, we see here intermediate levels of economic development. So in a sense, this scenario is probably better for the world compared to A2, but it's also less rapid and more fragmented in terms of the technological transfers compared to B1 and A1. And so overall, we see less less economic development compared to B1 or A1. And so under all these storylines, then the world is divided into several major regions, and these regions are essentially defined based on the level of economic development, and then those families of scenarios, they're really fine-tuned for the geographic differences of all these regions. Like we see here the OECD 90 region. Those are the most developed economies, including the United States and Canada, countries of the European Union, and Australia, and Turkey is here as well. And then there are transitional economies of the former Soviet Union and Eastern Europe that are shown here in blue. And then we see here countries of Asian countries in light green. We see here both Southeast and East Asia lumped together, but Japan is with OECD, of course, as a much more developed country. And then we also hear the developing countries within South America, Central America, and Africa. So within each of these regions, then the development scenarios are tuned up for the specific for those geographic regions for each of these families of scenarios A1, A2, B1, and B2. Now, the RCP approach is fundamentally quite different compared to stress. Again, they work along those broad storylines describing what would happen to the world if we do this and this and this. Like what would happen if we have, certain size of population, of what would happen with our energy transition, or what kind of land use changes would be contributing to climate change. So differently from stress, RCPs are developed by different modeling groups. They don't have kind of the same coherent framework that brings all the scenarios together. But they're not necessarily as comparable as stresses, but they tell us different, essentially, socioeconomic stories for the world to guide our mitigation and adaptation efforts and guide our climate change mitigation analysis. So you would see some overlap between stress and RCPs, and let's look at those storylines. Now, the key differences between the stress scenarios and RCP scenarios is that RCP, the representative concentration pathways, they don't have fixed sets of assumptions related to the population growth, economic development, or technology associated with each of those RCPs. So those are essentially like broad storylines for the world, and they are not specific as threats to specific, specific assumptions about globalization, for example. Many different socioeconomic futures are possible, of course, and they can lead to somewhat the same level of radiative forcings. So we're going to look at the similarity of like RCP 8.5 and stress A1FI. So kind of can arrive to the same futures through different combinations of those anthropogenic forcings. So here are some examples of those representative concentration pathways that are explored in the fifth assessment report of the IPCC. And they're listed here from sort of the best case scenarios to the worst case scenarios of the world, with the projections of global warming by the middle of the century and by the end of the century. So we could still, in theory, have the RCP 2.6 if we really have dramatically changed our climate policies and did everything right and completely stopped our emissions. We could then contain our warming under 1 degree by the middle of the century, or probably more realistically, like under RCP 4.5, we could go to 1.5 degrees by the middle of the century. But then as we go further, we actually see warmer and warmer world depending on the choices of those climate policies. And then by the end of the century, we see essentially very stable world under RCP 2.6, where we would just have this 1 degree warmer, and we would start stabilization, and the temperature would not increase anymore, going all the way up to 3.7 or almost 4 degrees temperature increase by the end of the century if we actually go with RCP 8.5. So let's take a look at each of those representative concentration pathways, or RCPs, a little bit more in depth. So this is how they would actually look on the graph if we plotted them all up to the end of the century. You would see that right now, unfortunately, we are very much on target with RCP 8.5. Both in the United States and worldwide, we really need to work very, very hard on getting rid of fossil fuels and moving to our with our energy transitions to renewable energy as soon as possible, because this is really the only way how we can move from this blue line representing RCP 8.5 to hopefully, like at least something like this. But of course, the best case scenario would be for us something like RCP 3 or RCP 2.6, leading to stabilization after the middle of the century. So let's start with this best case scenario. So the RCP 2.6, this is a low emission scenario, which is leading to stabilization within the next 10 years. This is the scenario that was developed by the PBL Netherlands Environmental Assessment Agency. This is essentially an equivalent of our EPA in the Netherlands. And so under this scenario, we see decline in use of oil, very low energy intensity of our economy, the world population that will stabilize at not more than 9 billion people by the end of the century. We would also see the use of croplands increase due to the bioenergy production. Biofuels are going to be a part of this energy package. And under this scenario, we also see more intensive animal husbandry. So it's not necessarily great for the animal rights, but from the perspective of the emissions, it actually can be achieved if we do this right with correct use of technology. Under this scenario, we would capture most of our methane emissions, especially from agriculture, from this very high-tech agriculture. So the methane emissions would be reduced by 40%. We would also see the CO2 emissions staying essentially at the same level as now till this year, right? And then they will start declining, and we're essentially entering in the drawdown we start throwing down those emissions from the atmosphere into the carbon sinks. So it requires lots of carbon sinks, and the CO2 concentrations would then peak despite the reduction of our emissions. So our emissions need really to stop right now. And even so, even if we stop our emissions right now, the carbon dioxide concentrations would still continue growing till 2050, and then they would stabilize and we would see some modest decline. So they would essentially go back to kind of 400 particles per million. We are a little bit above 400 particles per million right now. And so the idea is that this is where we are going to stay all the way through the end of the century. So this is, as you can see, it's probably not the most realistic, but this is definitely the best scenario for the world. Another representative concentration pathway was developed by the Pacific Northwest National Laboratory here in Corvallis in Oregon, and this representative pathway 4.5 focuses on what the world would be if we were achieving the intermediate level of emissions. This scenario is actually quite comparable to the B1 stress scenario. So you probably remember that this is a scenario that emphasizes globalization with lots of international collaboration, and it also focuses on environmental priorities over economic priorities. So with this, we should expect much lower energy intensity. This scenario really emphasizes the importance of forest carbon sinks, so that lots of strong reforestation would go all over the world, and we would really capture lots of carbon thanks to the reforestation. It also emphasizes, very quick departure from fossil fuels, so very low energy intensity of our atmosphere, intensity of our use of fossil fuels, the decline of emissions of carbon into the atmosphere. And this scenario also suggests a decrease in the use of croplands and grasslands due to yield increases and dietary changes. So under this scenario, we're really expected to eat significantly less meat. We would see very stringent climate policies with specific measures being attached both at the national and international level, and we would also see here very stable methane emissions. So under these scenarios, the CO2 emissions would increase only slightly during the next few decades, and then they will start declining, and they basically would start declining in the middle of the century. The next representative concentration pathway, the RCP6, was developed by the National Institute for Environmental Studies in Japan. Again, those are all very independent storylines developed by different interdisciplinary groups of scientists in different countries. And this RCP is quite comparable to the stress scenario B2. So you remember that this is more fragmented, regional world with various national agendas, but also with strong focus on the local and national sustainability. So this future is consistent with still presence of fossil fuels. So we are not going away from the fossil fuels, and we're actually seeing here intermediate energy intensity, but we also see the growing use of renewables. In terms of the fossil fuels, this is especially continuous use of natural gas, right? So under this scenario, we see the increase in use of croplands, but also decline in use of grasslands, stable methane emissions, and the CO2 emissions basically would continue growing all the way through 2060. And we would see, the maximum emissions, the emissions higher than today by 75% by 2060. And then the emissions would stabilize, and then they would decline, and essentially they would be 25% above what we have today by the end of the century. So it's a much later stabilization with much later transition towards more renewables. Okay, the next storyline is really where we're heading right now, unfortunately. And this is really the storyline where we don't want to be, because this can be quite deadly for us as a human civilization. So this is RCP 8.5. This is a high emission scenario. It was developed by the International Institute for Applied System Analysis in Austria. And this is quite consistent with the stress scenario A1F1 suggesting, but it has even higher population growth. So this scenario is suggesting 3 times higher emissions of carbon dioxide than now by the end of the century. Also, increase of the methane emissions, increase of the use of croplands and grasslands driven by the increase of the population. The world population reaching 12 billion people by the end of the century. Under this scenario, we also see a lower rate of technology development, less technology transfer, heavy reliance on fossil fuels, no implementation of climate policies as they were negotiated through Paris agreements and other international agreements, and high energy intensity. So as you can see, this is a pretty devastating scenario for the planet and for all of us, and we really need to work. We need to pull our sleeves and work as hard as possible to really pull us away from this storyline as quickly as possible. So this map of the world and this graph compare the RCP 2.5, 2.6, sorry, this is the kind of the lightest emission scenario with stabilization by the middle of the century, the RCP 2.6, the kind of the coolest scenario for the world, versus RCP 8.5 that you see at the bottom where we are going to see a very high temperature increase all over the world already by the middle of the century, and much worse, maybe 4 degrees or more by the end of the century. This is how these RCPs are actually looking. This is our historical data all the way through 2000. And as we're diverging right now, unfortunately, like we are very much somewhere here on track with RCP 8.5. So let's hope that we would end up somewhere in the middle. I think RCP 2.6 is by now extremely unrealistic, because every year we are really losing this time frame, that window when we need to act as quickly as possible. But not everything is lost, and so climate policies do matter. Climate policies can make a huge difference, and so I'm hopeful that we would end somewhere in between, probably somewhere closer to the middle. But as I said, like we need to work as the entire world, and we need to work very hard here in the United States and to help to extricate us from the RCP 8.5. And this completes Unit 2, Climate Modeling. So I wanted to remind that our readings this week and during the next couple of weeks include Chapter 4 from the first volume of the National Climate Assessment. And we are continuing to work with our electronic book, Climate Modeling Primer. And by now you should have finished with Chapter 1 that was a part of the previous unit. This week we are reading Chapter 2. Chapter 3 and 4 are optional. If you have time, read them or at least skim through. It will help you to understand how climate modeling has evolved to where it is now. And of course, we would finish with Chapter 5 and Chapter 6 during the next 2 weeks. Now, I also wanted to ask you to read the descriptions of the stress and RCP scenarios, and those links are provided on the Blackboard as well as in the syllabus. That will help us to understand how the scenarios actually work. And on those websites, you would also find some data associated with each group of those scenarios for the world and for different regions of the world. As always, if you have any questions, please send me an email or come to see me during our Thursday tutorials at 10 a.m. and also during my office hours on Fridays, also at 10 a.m. from 10 a.m. to noon.